The complexities of extracting resources from celestial bodies would be explored in this video. The profound implications for humanity's future resource needs and technological advancements would be illuminated for the audience. The increasing demand for rare earth elements, REEs, and precious metals, coupled with dwindling global reserves, necessitates the exploration of new sources and more sustainable mining practices. This is driven by the critical role these elements play in technologies like renewable energy, electronics, and electric vehicles. REEs are essential for permanent magnets in wind turbines and electric vehicle motors, as well as components in batteries and other clean energy technologies. Precious metals like platinum and palladium are crucial in catalytic converters and other applications. The transition to a low-carbon economy and the proliferation of electronic devices are significantly increasing the demand for these materials. Efforts are underway to identify and develop new RE deposits, including exploring unconventional sources like extinct volcanoes. Recycling e-waste and other industrial byproducts can recover valuable REs and precious metals. Developing more environmentally friendly mining techniques and processing methods is crucial. Fostering collaboration between nations to secure responsible and sustainable supply chains is vital. In essence, the challenge lies in balancing the increasing demand for these essential resources with the need to protect the environment and ensure a stable and secure supply chain. Precious metals like platinum and palladium are crucial in catalytic converters and other applications. There's big money to be made in asteroid mining. Asteroids contain vast quantities of valuable resources like platinum, gold, and other critical materials, potentially worth trillions of dollars. While the economic potential is immense, the technology and logistics of asteroid mining are still under development. Asteroids contain significant amounts of precious metals like platinum, gold, and other valuable elements like nickel, cobalt, and rare earth minerals. Some estimates suggest that a single platinum-rich asteroid could contain more platinum than has ever been mined on Earth. These resources are not just valuable for their monetary worth, they are also crucial for various technological applications and could potentially revolutionize industries on Earth. Asteroid materials could be used to build infrastructure in space, such as habitats, spacecraft components, and propellant depots, potentially reducing the cost of space exploration. Extracting resources from asteroids requires significant advancements in robotics, propulsion systems, and materials processing. Launching and operating mining equipment in space is expensive, and the cost-effectiveness of asteroid mining is still under evaluation. While asteroid mining could potentially reduce the demand for terrestrial mining, it's crucial to consider the potential environmental impact of mining operations in space. The legal and regulatory framework for asteroid mining is still evolving, and there are ongoing discussions about who owns the resources and how they should be managed. Asteroid mining could alleviate resource scarcity on Earth and provide a sustainable source of valuable materials. Successful asteroid mining could create new industries, generate wealth, and potentially lead to a more prosperous space economy. Missions to study asteroids like NASA's Psyche mission are crucial for understanding planetary formation and the origins of our solar system. The term Goldilocks zone, when applied to asteroid targets, specifically near-Earth asteroids, NEAs, refers to their accessibility for exploration and resource utilization. It's not about temperature like the planetary Goldilocks zone, but rather about the ease and feasibility of reaching and interacting with these space rocks. This zone is defined by factors like orbital proximity to Earth, size, and composition. The Goldilocks zone of asteroid targets is therefore a balance between accessibility and potential reward. While some NEAs might be easier to reach than others, those offering the best combination of resources and scientific value are often considered ideal targets. NEAs within this zone are relatively close to Earth, making them easier and cheaper to reach with current and near-future space technology compared to asteroids further out in the solar system. Overcoming challenges in space exploration, such as zero gravity, extreme temperatures, and radiation shielding, requires innovative engineering and specialized materials. Zero gravity poses challenges for physical tasks and fluid management, requiring solutions like specialized equipment and careful water handling. Extreme temperatures, both hot and cold, necessitate the use of robust materials and thermal management systems. Radiation shielding is crucial for protecting astronauts from harmful solar and cosmic radiation, with solutions including dense materials, magnetic fields, and electrostatic shielding. Astronauts use tethers, harnesses, and specialized equipment to anchor themselves and manipulate objects in zero gravity. Deep space environments can be extremely cold, requiring specialized materials and thermal management systems like cryogenic connectors. Water extracted from asteroids could sustain human presence beyond Earth, providing both drinking water and the components for rocket propellant. This capability would enable a transportation network throughout the inner solar system, with refueling depots reducing mission costs and expanding exploration range. Deep space exploration and establishing permanent lunar and Martian bases are major goals of current space programs. These ambitious endeavors rely on developing new technologies for in-situ resource utilization, ISRU, advanced robotics, and sustainable life support systems. The focus is on creating self-sufficient, long-term settlements, leveraging lunar resources to fuel further missions, including those to Mars. By focusing on these key areas and technologies, space agencies and private companies are working towards a future where humans can not only explore deep space but also establish permanent settlements on the Moon and Mars. Rising temperatures on asteroids, particularly during optical mining, can significantly impact mining operations by causing thermal spalling, potentially fracturing and weakening the asteroid material. This could hinder the efficiency of scraping or strip mining, where valuable ore is collected after being scraped or pulled from the asteroid. The process of heating and cooling can also create stress and pore pressure within the asteroid's structure, further contributing to material failure. In conclusion, rising temperatures on asteroids pose a significant challenge to mining operations. Understanding and mitigating the effects of thermal spalling and other temperature-related phenomena is essential for the future of asteroid mining. The need to deal with fractured and weakened material could significantly impact the efficiency and cost-effectiveness of asteroid mining operations. If tunneling into specific veins of valuable substances is planned. The legal and ethical dilemmas surrounding property rights in space primarily revolve around the interpretation and application of the Outer Space Treaty of 1967, particularly regarding national appropriation, resource utilization, and the rights of private entities. While the treaty prohibits national claims of sovereignty over celestial bodies, it leaves open questions about ownership and exploitation of space resources by both nations and private companies, leading to ongoing debates and potential conflicts. The Outer Space Treaty, OST, explicitly prohibits national appropriation of outer space, including celestial bodies. However, the treaty is silent on the ownership of objects launched into space and materials extracted from space. The commercialization of space raises ethical questions about equitable access to space resources, the potential for exploitation, and the preservation of the space environment. Financial feasibility. Space ventures are high risk, with long lead times and heavy capital investment, and that is no different for asteroid mining projects. These types of ventures could be funded through private investment or through government investment. In the next 20 to 50 years, the first successful asteroid mining operation is likely to revolutionize resource acquisition and space exploration. This endeavor will likely involve robotic equipment, solar-powered machinery, and resource extraction techniques similar to those used on Earth, potentially leading to a new era of space-based industry and resource management, while also raising questions about its economic and geopolitical impact. In essence, asteroid mining represents a significant leap in human technological and economic capabilities, with the potential to reshape our relationship with space and the resources it holds. The initial phase will likely involve identifying and characterizing suitable asteroids, followed by developing and deploying robotic mining systems. Extracted materials, particularly water ice, could be processed into rocket fuel, hydrogen and oxygen, for in-space refueling, enabling further exploration and reducing reliance on Earth-based resources. Successful asteroid mining could establish a new paradigm for resource acquisition, potentially alleviating resource scarcity on Earth and fueling further space exploration and development. Asteroid mining will likely drive further advancements in robotics, materials science, and space transportation. International agreements and regulations will need to address ownership, resource extraction, and the potential environmental impact of space mining.